This is slide number 36 and I am your presenter Asloob Mudassar. Let's talk about the integral theorem of Helmholtz and Kirchhoff. An optical disturbance U is incident on surface S from outside encompassing volume V. Look at this surface. So you see that I have written capital S outside this surface. So this surface S encompasses the volume capital V, and there is a point of observation P naught. We actually want to calculate the field U, capital U, which is incident on the surface capital S, and we want to from outside, and we want to calculate the contribution of that field at the point of observation P naught. And around the P naught we have drawn a sphere of radius epsilon, and the surface of that one is S prime. So S prime is the inner surface of that sphere, and there is another point shown, which is P1 point at a distance r01 from the point P naught, and you know that n are the normal vectors on the surfaces. You can see that these are the normal vectors I have drawn on the capital surface S, and I have also drawn this on the inner surface S prime. So let's do some calculations using this figure. We want to find U of P naught, that is U of P naught, an optical disturbance at the point of observation point P naught located within the surface capital S. Let's assume that another disturbance generated by a hypothetical point source located at the point of observation P naught is incident on the surface capital S from within with a value equal to G. And on the geometry, I have written that geometry for the calculation of a field at a point P naught due to the field U incident at the surface capital S. So you see in the paragraph that just I have read means that we are assuming a hypothetical point source capital G located at the point P naught, and of course this source will generate spherical waves all around, and those spherical waves will also hit the surface capital S, and also on the hypothetical surface capital S prime, which is lying within that one in the form of a sphere. Okay. The net contribution due to these two fields, so there are two fields that will reach at the point P naught. One is the field U, capital U, and the other originating from the point P naught is the field capital G. So the net contribution due to these two fields through the surface S is related through a well-known theorem known as Green's theorem, which is given by. So in the Green's theorem we are relating these two fields, one from inside the surface and the other from outside the surface, and the total volume V that encompasses the surface capital S is the volume capital V. So on the left hand side we have the triple integral indicating that we are talking about the volume integral. On the right hand side we have the double integral, which is the surface integral. And you can notice the arguments that the volume integral has the argument U into del square G minus G into del square U. And on the volume surface integral on the right hand side we have capital U multiplied by the partial derivative of G with respect to N minus G into the partial derivative of U with respect to N. So if we could evaluate this integral, we can find out the field contribution to the surface S. So, and you know that del square G and del square U on the left hand side in the volume integral can be calculated using the Helmholtz equation. So let's proceed. For this integral to hold, U and capital G are required to be single valued with continuous second order derivatives to exist within and on the surface S. So partial derivative of J with respect to N and partial derivative of N with respect to N are the normal or the directional derivatives, where N is a unit vector on the surface S pointing towards the point of observation. The value of the field G at the arbitrary point P1 lying within the surface S at a distance r01 from P0 is given by. So you see that you can look at the point P. Now we want to calculate the contribution of the hypothetical point source located at the point P0, and we want to calculate its contribution at the point P1 located at a distance r01. And the contribution of G at a point P1 is e to the power iota k r01 over r01. The value of the disturbance capital G blows up at the point P0 because r01 goes to 0 at that point. To exclude the contribution of a point P0, we draw a sphere of radius epsilon centered at point P0. So you can see in the figure that we have drawn a sphere of radius epsilon centered at the point P. So this is a sphere, you know, and we have also shown the internal surface of that sphere is S prime, and where the unit vector is also n hat is shown towards the point P0. U and G being optical disturbances will satisfy the Helmholtz equation as given. So if you satisfy the value of capital U and the value of capital G in the Helmholtz equation we have discussed earlier, then you know that you come up with the equation number 16, which is del square plus k square within the bracket operating on capital U is equal to 0, and similarly we have del square plus k square operating on the field capital G will give you 0. So you have equation 16 and 17. So these equations will help us to eliminate the del square from the previous equation, that is from this equation, that is from the Green's theorem equation. We can replace del square G and del square U using the equations number 16 and 17. So taking out del square U from equation number 16, we have a minus k square U, and del square G from equation 17, we have del square G is equal to minus k square capital K square G. So substitute this value in the volume integral, you see that the argument of the volume integral can be cancelled out because they are the same with the different opposite polarities, and we get the total volume contribution from the volume integral equal to 0. And then we have the integral over the total surface ST. T stands for the total and S is the surface. So this now we have the double integral on the total surface, and you know that this includes capital G and the partial derivative of G and capital G and the partial derivative of U in equation number 18. So S is the total surface including two surfaces. One is the capital surface S, which is the outer surface, and the other is the S prime surface, which is located within the capital S surface in the form of a small sphere of radius epsilon naught centered at the point P naught with the corresponding total volume. The total volume included by these two surfaces is regarded as Vt, that is the total volume. So you know that since the volume integral is 0 in equation 18, we are left with only surface integrals. So this ST will be divided into two surfaces. One is the S prime surface as in equation number 19, S prime surface, the other is the S surface. So this integral will sum up over these two surfaces, and of course on the left hand side in equation 18 we have 0, which we have represented on the right hand side in equation number 19. So we have to solve these integrals. We have to find out the value of integral on the right hand side. So let's try to solve the integrals on the left hand side, which is the signal, which is the double integral over the S prime surface. The value of G on the surface S prime is given by, and you know that this S prime surface has a radius epsilon from the point P naught. So G of epsilon will be equal to e to the power iota k epsilon over epsilon. And the partial derivative of G with respect to n is evaluated using equation number 20, which is given below in equation 21. So these are simple mathematical equations from the calculus. Now we have equation number 20 and equation number 21. And we can use these equations in order to evaluate the integral over the surface integral over the surface S prime. And you know that by definition of the directional derivatives, we have a partial derivative of epsilon with respect to n is equal to cos or cos of the angle between the unit vector n and the epsilon, and you know that the angle between them is 180 degree, which is pi, so cos of pi is equal to -1. So this has been used in equation 21 to obtain it in its present form. Okay, now we are going to evaluate the integral, the double integral over the surface S prime. So what we do is that since we have to exclude the point P naught, because point P naught is the point where the signal, where capital G is going to be infinity, so we eliminate, so we want to get rid of the contribution of the of this integral at the point P naught. So let's put a limit that epsilon goes to 0. And we have the same the double integral over the surface S prime, and we have now the values of these variables, that is u at the point P naught and then u at the point P naught with its derivatives. So now we have u of P naught into the partial derivative of g with respect to n minus g into the partial derivative of u evaluated at P naught with respect to n. So now we have to substitute these values. We have taken u of P naught as such, and we have substituted the values of curly g over curly n from one of the previous equation, that is equation number 21. And we have written capital G, we have replaced capital G by its value from equation number 20, and then of course the rest of the partial derivative of u with respect to n is the same. Now you know that since we have in the integral chosen, we have chosen the point P naught, a particular point, so under that condition the integral will be independent, the argument will be independent of the integral, and we have written the integral on the right hand side. So the surface integral on the right hand side over the surface S prime is on the rightmost side of this expression in row number 2. Now what we do is that we have substituted these values in equation in row number 2, and then we have rearranged them in row number 3. And you know that now we have to apply the limit epsilon goes to 0, but before we apply the limit, we are sending 4 pi epsilon square, we are multiplying the terms within the parentheses by the value 4 pi epsilon naught square, which is the area of the sphere of the surface S prime. So when these will multiply, you see that only first surface on the on this limit will survive, the rest of them will be equal to 0 due to the limit. So we have equal to 4 pi u of P naught in equation number 22, the last point. So what we do is that so let's read the statement. For the integral over S prime in equation number 19, we have to choose epsilon goes to 0 in order to exclude the point P naught. Now using equation 22 into equation number 19 gives, so we are using this final relation in equation number 19. So this is equation over 19. We have evaluated the integral, the surface integral, double surface integral over the surface S prime. We have evaluated it, and its value is 4 pi u of P naught. So what we do is that we send this integral, for example, we send we send this integral on the left hand side, or maybe on the right hand side, and u of P naught on the left hand side or on the right hand side, because we have evaluated this one. So the negative sign that will appear by shifting this integral, we shall multiply that negative sign to these the arguments of the surface integral over the surface S, and the order will change as we have shown in equation number 23. So we have u of P naught, which is the field at point P naught, which we wanted to evaluate, is equal to 1 over 4 pi into the surface double integral surface integral over the surface S. And we have, you know, that they change the order of the arguments in the parentheses, that is we have taken g curly u over curly n minus u into curly g over curly n. So equation 23, you know, that is very in a pleasant form, that gives us the expression that we can evaluate the field which was incident from outside on the surface capital S. We have its expression at the point P naught in terms of the integral in equation number 23. The surface S is mathematically undefined, and the value of G will vary from point to point on this surface. However, if we assume that the surface capital S is a surface of radius r centered at point P naught, then capital G will have the same value for all points on the surface S, and in that case equation 23 takes the following form. So equation number 25 was written from equation 20 number 3. Assuming that this surface capital S now has a shape of the sphere of radius r. So we are going to use the value of this field over here. So u within that integral is given by its value, which is e to the power iota kr divided by r, a spherical wave at a radius r. And then we have this the partial derivative of G. This is actually capital G value, e to the power iota kr over r, because now the contribution of the capital G, which was originating from the point P naught at the surface capital S, which is now in the form of a sphere of radius r, the value of capital G on that surface is now e to the power iota kr over r. And here we have in the form of the argument, you know that here in equation number 23 we have a partial derivative of G with respect to n, and we have substituted over here the capital value of G, which is e to the power iota kr over r. Equation number 23 and 24. So these two equations, that is equation number 23 and equation number 24, are very useful, and we shall be using these equations repeatedly in order to find the value of the field at the point P naught. So equation 23 and equation 24 are known as the integral theorem of Helmholtz and Kirchhoff, and we shall be using these equations. So here this is the end of slide number 36.